Hi, my name is Trevor. I'm the author of Lamorna Engine, a light 3D game engine featuring a software renderer which you just saw running. Today I'd like to talk about the engine's collision scheme. I found collision detection one of the hardest game systems to write, even more so than rendering. Whereas the occasional graphical glitch may be tolerable, collision is unforgiving. Pushing through a wall or falling through the floor is a deal breaker for player experience. Lamorna Engine has a simple but robust collision scheme. Simple in that it only supports linear collisions against axis-aligned surfaces, but robust in that it uses an internal fixed point format to give strong guarantees about precision. The process is multi-threaded and uses a broad phase check against a bounding volume hierarchy to quickly discard non-colliding entities. Entities participating in collision checks are expressed as axis-aligned bounding boxes with a position and extent. This makes a preliminary overlap test as simple as checking the sum of the extents against the absolute difference between the two positions for each axis. The position and extent are in fixed point format with 16 bits of decimal precision, with all calculations being done in 64-bit. For some elements, like the blocks that compose the game world, the bounding box is a direct expression of its shape. For other, more complex models, it is simply an approximation. The collision system defines colliders and collidees, where colliders are dynamic elements like players, monsters, projectiles and such, and collidees are the mostly static world elements. They are identified in the entity component system with their respective components. Some of the moving elements are both colliders and collidees, the players and monsters, for example. The collision system's modus operandi is to take each collider in turn and collide it against each collidee that falls within its purview, cool word, adjusting the position of the collider as needed, but treating the collidees it encounters as static. This makes for a straightforward scheme and works perfectly for simple collision encounters such as player versus static world, projectile versus moving entity, but starts to break down when more complicated interactions between two or more moving objects are required. The engine identifies three types of collidees: static, moving, and rotated. Rotated collidees are those entities whose bounding box is not axis aligned. In the demo, the only example of these are the bounce pads. Processing them requires mapping the bounding box with an orientation matrix. Moving collidees are the platforms. Their collision code requires some special handling to make it work. And static collidees are everything else, remembering that my scheme treats all collidees as static by default for the purpose of collision, even though they may actually be moving. So for example, the player's movement is taken into account when it is a collider, but not when it is a collidee. Let's look at the process of collision detection. The collision process opens with a pre-step that bins all dynamic collidees, those whose position can change each frame, into the static collidee bounding volume hierarchy. This static bounding volume hierarchy was created at setup by binning all static world elements into a regular 3D grid, and then adjusting the bounds of each node of the grid to fully contain its set. This loose grid approach creates nodes of different sizes, but means each colliding element is present only once, which I felt was a win over a tight bounding volume hierarchy where collidees spanning multiple grid nodes are duplicated across those nodes. There are not nearly as many dynamic collidees needing binning in comparison to static collidees, so the runtime binning is not particularly time consuming. So here's the code that performs this binning. This code bins the three different collidee types present in the entity component system separately. We loop over each grid node, then each entity within the collidee type, and bin the entity if its bounding center is contained within the node extent. We write sufficient data to collide the entity into a common array and bin an index to that in the relevant node. These few lines of code constitute the bounding box check, comparing the absolute distance between the entity center and node center against the node extent. Since this is a loose bounding volume hierarchy, node extents may overlap. So to prevent binning the same entity across multiple bins, we mark the first binning instance in a bit array and check against that. Once all the entities are binned, we need to readjust the bounding extents of the node to accommodate them. We keep the static extents we computed at setup and simply adjust them each frame, and that's what this code block here does. So now our bounding volume hierarchy is ready for use for this frame's collision process. So let's look at that. The collision process is threaded, where each thread is passed a list of colliders to check. After some initialization, these outer loops are fetching the collider data from the entity component system. The movement system has been run prior to collision and has generated a displacement vector for each moving entity, which describes its potential movement for this frame. Here I convert this displacement into a normalized direction vector and a magnitude. I found this approach easier to work with and more robust. Consuming the movement vector as the collision steps proceed becomes simply a case of decrementing the magnitude, and the normal vector can be clamped to an axis without loss of precision. I store this data in a local collider structure. The next step you could characterize as broad phase collision detection. Let's have a look at that. We check the collider against the bounding volume hierarchy using a conservative bounding box that contains the extent of the collider's potential movement, given that collisions will deflect it, and outputs an index list of potential collidees for further narrow phase analysis. Here we use SIMD to process 4 grid nodes at a time. We broadcast the collider data out ahead of our loop, and then within the loop fetch out 4 node positions and extents into this array of structures and transpose it into structure of array form for vector processing. Bounding box check is done with vector intrinsics wrapped in these overloaded operators. It makes the code look and flow like scalar operations. And we use a sparse array compression scheme on our result vector to output the index list. From the list of potential nodes the collider intersects with, we now generate a list of potential collidees by performing the same process above on the collidees within the nodes. Our output is a short list of potential collidees, typically less than 4. If the potential node or collidee list is empty, our work on this collider is done and we can move on to the next one. This final block of code sorts the potential collidees into their respective types. So returning to our main collision code, now we can move on to the narrow phase collision. The narrow phase is iterative, checking the collider against each potential collidee in turn, adjusting its position and direction, then rechecking until its movement vector is consumed. No more collisions are detected or an upper iterative bound is reached. The narrow phase collision code comes in 3 flavors for the 3 different collidee types we mentioned earlier. We will only look at the static code here. Collision checks in the narrow phase are performed by expressing the collider as a point and directed line segment, and the collidee as a series of axis-aligned slabs with its extent summed with the extent of the collider. Intersection intervals are generated for the line segment against each axis slab and composited into a final interval for each bounding box, the smallest valid one being the collision interval for the set. If there is a valid intersection, we write the details of the collidee out into a collision data structure. Returning to our main loop, we exit our loop if there has been no collision, else ignoring this block of code for now, we step the collider's position to the intersection point using this the t interval that we have just calculated. Now we select a number of we select from a number of collision responses based on the collider and collidee type. So let's rise up and look at those. So the movement vector of the collidee is adjusted depending on the type of collision response required. For deflection, which yields the sliding behavior you want for natural moving entities like the player and monsters, the movement vector is set at a tangent to the colliding surface. For reflection or bouncing, the movement vector is reflected about the surface normal. The collider can also be brought to a stop by the collidee, in which case the movement vector is set to 0. The type of collision response for the current collider-collidee pair is obtained from a lookup table. Working with axis-aligned boxes means the collider's position can be clamped to the colliding axis, offset by a small epsilon to push it off the surface, which is a big aid to fidelity. So returning to our loop, collision response. So the collision process iterates, adjusting the position of the collider until there are no more collisions, the movement vector is consumed, or the iteration count is exceeded. When done, the updated direction vector and magnitude are restored as a displacement vector to be added to the entity position in a later step. As a final point, some game entities need to be able to step or rise over low obstacles for continuity of motion. This is done by running a second narrow phase collision pass for a slightly elevated copy of the collider. And if that copy can proceed where the original is blocked, the entity is allowed to surmount the collidee. So the output of the collision process is a list of valid colliders and collidees with their contact points, which can be passed by the game logic systems for further collision outcomes. Well, that concludes our look at collision detection. Be sure to check out my code reviews of other engine systems, visit my website, and follow me on Twitter. Thanks for watching.